Yes, by the continuation of the last lecture in current electricity, now we are going to discuss another concept in current electricity, that is Kirchhoff's laws. So, Kirchhoff's laws, how Newton's law is very important for Newtonian mechanics. Is similar to any electrical circuit, the Kirchhoff's laws are very important. So now you please see that the first rule, that is called junction rule or current rule. It is based on conservation of charge. It is based on conservation of charge, conservation of electric charge. What this rule says, algebraic sum of the charges meeting at any junction will be zero. That means algebraic sum of the electric current, or that is we can say that algebraic sum of the current meeting at any junction will be zero. So, or the same can be written as, we can write that the current, sum of the current towards the junction is equal to sum of the current is away from the junction. Okay. The sign convention is the currents which are coming towards the junction is taken as to be positive, and which are going away from the junction is taken as to be negative. So that is the general sign convention what they used here. The total charge at the junction will be zero because there is no accumulation of the charge here. Therefore, as per this equation, sum of the current inward. So for example, sum of the current inward is I1 plus I2, that is equal to the current which is going out, sum of the current going out. Okay. So the second law is voltage rule. So voltage rule or loop rule. Okay. So what this says, algebraic sum of the voltage and EMF in any closed loop will be zero, and this is based on, this will be based on, or the same can be written as, we can write that sum of this V is nothing but IR in the each branch of the circuit. This is EMF, that is equal, this is algebraic sum, so EMF of the battery. So this law is based on conservation of energy. So this law is based on conservation of energy. So this is the two important thing what we must in we must know in that. Here also the sign convention is there. So therefore sign convention. So sign convention is for voltage V is equal to IR for this term, and for EMF E. So here also I can say some cases it will be positive, some cases it will be negative. So just see that suppose you just see that this is the given resistor, the current is going from positive terminal to negative, that means from higher potential to lower potential. You know that current always going from higher potential to lower potential. Suppose if you are going along this direction, that means your direction is along the current direction, at last you are crossing the negative terminal, therefore the product of current and resistance will be negative. Suppose the same arrangement, you just see that this is the given resistance, current is going. We know that current always go from higher potential, lower potential. Suppose you are going opposite to the current direction. If you are going opposite to the current direction, the product, at last you are crossing the positive potential, therefore the product will be plus IR. The product will be plus IR. So this is the thing what you have to be keep in mind. In the case of a potential, suppose this is the cell, so positive, negative, and this is EMF. If you are walking along this direction, okay, so this is your direction of movement in the loop or circuit. At last you are crossing the negative terminal, therefore the EMF sign will be minus E. So similarly here you just see that. So this is the cell, so plus minus. You are walking along this direction. At last you are crossing the positive terminal of the battery. Therefore, in this case, the sign of EMF will be plus E. So this is the sign convention what we used in the case of voltage rule. The next one is is another important question, that is Wheatstone's bridge. So Wheatstone's bridge is Wheatstone's bridge. Yes, we just see that it is the some arrangement of a network of the resistors. So this is say this is resistance R1, this is R2, and they are arranged. This will be, say for example, R1, R2, R3, R4, and this will be R3. So this is the arrangement of the resistance, and some battery of EMF is connected over there. So plus minus, this is some battery key, some current I is going from there to there. Yes, in between that a galvanometer of resistance G is connected. Yes, this is the arrangement of Wheatstone's bridge. Now you please see that how to use this Kirchhoff's law. So whenever some circuit resistance or battery resistance or any electrical circuit is given, the junction rule is used to reduce the number of unknown currents in the circuit. The voltage rule is used to find out the potential values. So now you see that, now you please see that this is terminal A and this is B, C and D. So this is the terminals. The current through this branch is taken as to be I1 and this branch is taken as to be I2. As we said, so this is current through the galvanometer is taken as to be Ig. The current through this resistance R2, as we said here, the sum of current inward, that is towards the junction, is equal to sum of the current outward. Therefore, at the junction B, the current in is I1. So the current inward is I1, that is equal to at B the current is current I1. The current which are going away is Ig plus this unknown current. So Ig plus, say this is current through this branch, some X, something like that. So this is some X. So what is the current through this branch? X means X is equal to I1 minus Ig. So this is the way how to use the junction rule to reduce the number of unknowns. So instead of X, I can write that has to be I1 minus Ig here. So this is the way how to use the junction rule here. So the main how many unknowns are there in the circuit, that many number of linear equations we have to be right. Now you see that at this junction D, the inward current is I2 and this inward current is Ig. Therefore, the current, sum of the current in is equal to sum of the current out. Therefore, the current through this resistor is nothing but I out equal to I in, that is I2 plus Ig. So using junction rule, we can reduce the number of unknowns. Now please see that whether you are taking clockwise direction or anti-clockwise direction, that is our choice. So for the convenience, I can take that is clockwise direction. So this is the direction of way how I am going in the loop. Once the direction is fixed, it should not change. It should be followed throughout the part of the problem. Yes, we should not change. One side is clockwise and another side is anti-clockwise. Like that, you cannot change. During this process, suppose you are getting current value as to be negative, which shows that the assumed direction and actual directions are opposite. So you can get the current in negative values also. So there is no problem in these applications of Kirchhoff's law. Now please come to this. So I am taking the loop for the loop. A, B, D, A. So loop means your starting point and ending point should be same. So now please see that this is my direction of movement. So therefore, my direction and current direction both are same. Therefore, the product will be negative. Therefore, minus I1 R1. And this also in the same direction downward for this loop. Therefore, minus IgG. And I am going opposite to the I2. Therefore, plus I2 is R4. So that is equal to 0. And similarly for the loop, because there is no battery, therefore EMF will not be there. That's why I am writing only the voltage term or product of current and resistance. So for the loop, for example, BCDB, yes, in this case, you just write the equation. Again, your direction, because you are going like this along this branch, you are going along the current direction. Therefore, I can write that minus R2 into I1 minus Ig. But here, you are going downward, but the current is going opposite to that. Therefore, positive sign. So yes, that is R3 into yes I2 plus Ig. Yes, you are also going from yes C to D, then D to B. Yes, to complete this loop, B to C, C to D, D to B. Yes, then you are going opposite to the Ig value. Therefore, I can write that the term IgG, the total term is 0 because there is no battery here with the EMF. So then now at balancing condition, at balanced condition, what is the meaning of balanced condition? Means the current through the galvanometer should be 0. The current through the galvanometer in the middle branch should be 0. That is Ig should be 0. When this is possible means we know that there is a current flow when there should be a potential difference. Therefore, the potential difference across the B and D, that is VBD, is 0, or we can say that VB is equal to VD. Under this condition, the current through the galvanometer is 0. So say this is equation number 1 and this is equation number 2. Substitute this condition Ig equal to 0 in these relations, then I can get minus I1 R1, this term equal to 0. This is taken to right side, minus I2 R4, that minus sign gets cancelled out. Therefore, I can directly write that as I1 R1, that is equal to I2 R4. So similarly, the second equation becomes Ig0, Ig0, Ig0. The remaining term is minus I1 R2, that is plus I2 R3, that is taken to right side, negative sign, that gets cancelled out. Therefore, I can get that I1 R2, that is equal to I2 R3. So this is the the expression after giving the putting these conditions. Now you please divide these relations. You just divide these two. Then I1 gets cancelled out. Therefore, R1 by R2, that is equal to R4 by R3. So this is the expression for a ratio of the resistance in balanced condition. But I can easily remember that just doing the opposite product. That means you just do the cross product of this, then we can get that as R1 R3, that is equal to R2 R4. That means under balanced condition, the product of the opposite arm resistance are equal. So that is the condition for balancing length in the wheatstone bridge. And there are some important special things we must remember here. That one is the first point is if the location of the battery and the galvanometers are interchanged, there is no effect of by interchanging galvanometer and battery. That means here the galvanometer is connected across BD and the battery is connected across AC. Now that will be reversed. That means this is the galvanometer. Yes, you just assume that the resistance R1 is there, R2 is there, and R4 is this will be R3. So this is the arrangement. Now the position of the galvanometer and the batteries are interchanged. So this is A, B, C, D. Now previously across BD galvanometer is there. Now it is interchanged to across AC. Previously AC battery is there. Now it is interchanged to BD. Under this condition the balancing condition will not be affected. So it is same as to be in the previous case. Therefore, in this case also the opposite product will be same, R1 R3, that is equal to R2 R4. That means by interchanging G and battery, galvanometer and battery, balancing condition remains the same. Balancing condition remains the same. So this is the important thing you must keep in mind. And next, another point is if these resistance R1, R2, R3, R4 all are in same range, equal range, then sensitivity will be maximum. Sensitivity, that means accuracy. Sensitivity will be maximum if all the resistances are equal in order. Okay, so that time we can get the maximum accuracy or sensitivity of the circuit. So this is the explanation for the wheatstone bridge. The next what we are going to discuss is its extension. Idea of the wheatstone bridge is extended to a practical device known as to be meter bridge. So meter bridge. So meter bridge. So this is based on our meter bridge is modified form of wheatstone bridge only. So therefore, the circuit diagram for that is given by yes, these are the yes, metallic strips. So just to see that you may yes, see this device in your laboratory. So this is the 1 meter as a constant ton or manganese wire. The why you are preferable for using as constant ton or manganese is already as explained in the previous lecture. So if you have if you want reason, kindly see that video. So this is the yes battery. Generally they are using in practical. They are using Lagrange cells. Okay. So now please see that. This is called a left gap and this is called a right gap. Yes, in this left gap, so say some known resistance R is connected. If you are putting box, we may assume that they are known resistance. That is our understanding purpose. So if you are putting like this, you may assume that they are unknown resistance, right gap. Now we see that this is terminal A and this is terminal B or joint B and this is terminal C. And from this is a center part of this metallic contact, there is a galvanometer and jockey J will be there. So this is a circuit is a diagram for the meter bridge. Just to see that, as we discussed earlier, R is equal to rho L by A. So therefore, the portion of the wire of length AJ, whose length is taken as to be L here, and this is taken as to be 100 minus L in centimeters. Okay. So the resistance offered by the portion of the wire AJ is taken as to be RAJ. The resistance offered by the portion of the wire JC is taken as to be RJC. Here I am going to define a small term called small r, that is resistance per unit length. Resistance per unit length. So this is the small r definition. So from this I can write that resistance is equal to small r into length of the portion. Small r into what, students? Length of the portion. So similarly, the resistance offered by this one. So let us consider this is a small r into the length of the portion AJ, that is nothing but L. So that is equal to, similarly here also, the length of the portion small r into a resistance per unit length. Small r into the length of this portion is R into 100 minus L. As we said earlier, you just see this equation, just do the opposite product. Therefore, this resistance and this will be cross multiplied, and this resistance and this resistance gets cross multiplied. So therefore, I can say that R into RJC. So therefore, R into RJC, that is equal to X into RAJ, therefore X into RAJ. So this is the easy way to remember the wheatstone bridge balancing condition when galvanometer shows the zero deflection. Yes. So now you please see that the substitute the value of this RAJ and here, therefore R into small r RAJC is there. So S 100 minus L that is equal to X into RAJ, that is small r into L. So you just simplify this, then we can get that R into 100 minus L, that is equal to unknown resistance X into L. So from this I can get to find out the unknown resistance, value of unknown resistance, X is equal to known resistance R into 100 minus L divided by L. So this is the required expression you may use in lab also. And moreover, also we know that this can be used to find out not only the unknown resistance, also to find out this is unknown resistance of this given wire X. Okay. So in the same manner, the same idea can be used to find our resistivity of this wire, resistivity of the material of this wire, rho. So you know that generally resistance equal to resistivity into length by area. So here I can in order to distinguish this balancing length with the actual length of the wire, I can use capital LA. So from this rho is equal to, I can write that from this rho is equal to X into A divided by L, where for a cross sectional area of the wire is generally pi r square. where small r represents area of cross section of the wire winding used in the given unknown coil S of length L. So these are the two important results are the things we can find out by using meter bridge apparatus. As we said earlier, by interchanging the position of the battery and the galvanometer, there is no change in balancing length. But here another important things we must be keep in mind that when these X and R are interchanged, the corresponding balance length gets interchanged. For example, here we can say that a small r gets cancelled out here, so I can write the same step here. So small r into 100 minus L, that is equal to X into L. This is the expression what we get. So just see that opposite product r into 100 minus L, that is equal to X into L. Now what I am going to do is just to replace this position of the X and R. That means suppose the left side X is placed, and right side R is placed, right side gap R is placed. So in this manner you are keeping in the left gap. Just see that this is the important thing you must know. By interchanging X and R, the corresponding balancing length also gets interchanged. Say for example, this is some 40 centimeter, this is obviously 60 centimeter. Now you interchange that, now this end AJ, so this portion of the balancing length, since X is interchanged, along the X side 60 is there, along the R side 40 is there. Now X and R are interchanged, then this corresponding balancing length also gets interchanged. Therefore this side it becomes to be 60 centimeter now, and this side it becomes to be 40 centimeter. So that is the important thing. Whenever the position of the R and X are interchanged, the corresponding balancing length also get interchanged. And the next point is, as we said earlier, if all these resistors are equal, then there will be a maximum sensitivity. Therefore, if you are getting the balancing length at the 50, then the sensitivity will be maximum, because at 50 the resistance offered by these two portions of the wire will be same because of the same length. So this is the another thing you must keep in mind for your as a theoretical discussion. So this result says that when X and R, that means unknown resistance and known resistance are interchanged, then balancing length also, then corresponding balancing length also, interchanged. So kindly keep this idea in mind. The next the next apparatus or the concept what we are going to discuss is potentiometer. So before that, you please kindly go through the notes and copy that. Continuation of that, we will discuss here is potentiometer. The another important topic is potentiometer. This is the another important area for the exam point of view. So now please see that is potentiometer. The first one what we are going to discuss is a principle of the potentiometer. So let us assume that there is a cell of EMF E. I can call it as this is a driver cell. So driver cell, so I can call that as to be ED. That is connected to say some key, and this is some variable resistance, say for example R external is connected to the potentiometer wire of length AB. Yes, this is the potentiometer. So this part is called a primary circuit. Yes, this upper portion of the circuit is generally called a primary circuit, which connects the potentiometer wire terminals AB with the driver cells along with the variable external resistance. In experiments, they can use the what it is called rheostat. Yes. Now that you just see that this is some some cell of EMF E is connected here, and there will be another key, so you can use it for that, or you can directly use G. For the principal part I am drawing this diagram, so you just see the portion AJ is called balancing length. As we discussed earlier, the balancing length is nothing but when the galvanometer deflection is 0, then that is called balancing length. Now you please see that when the position of the jockey is adjusted over the potentiometer wire AB, at a particular point the galvanometer deflection will be 0. Therefore, this portion of the wire AJ will offer some resistance, that I call it as RAJ, resistance offered by the wire portion AJ. Because of that resistance, the current delivered by the primary circuit, and this part is called a secondary circuit. Yes, this part is called a secondary circuit, and the upper part is called a primary circuit. Now a current is passing through this portion, so the potential drop across this wire is taken as to be V. The portion of the wire is V. So when the galvanometer shows zero deflection, means when the potential drop across this portion is same as to be the terminal voltage or the potential difference across the terminals of the given cell. So this is how the potentiometer is working. So what the principle says is, the principle is for steady current means constant current. For steady current which is passing through the uniform wire, the AB is the potentiometer wire whose length is taken as to be LAB, and the resistance of that portion of the total length of the wire is taken as to be RAB. So therefore, for the steady current through the potentiometer wire uniform cross section, so through the wire of uniform cross section, that means the area of cross section is constant, then the potential drop across the any 2 points is directly proportional to the balancing length of the given circuit. That means we can write that V is directly proportional to L. Therefore, we can write here also, so some proportionality constant K into L. This K is called potential gradient. So this K is called potential gradient. Okay. Now from this we can write that K is equal to V by L. So this is the one of the expression for potential gradient. And the another expression for potential gradient is, we know that it is directly proportional. Therefore, when you draw the graph between length and the voltage, balancing length versus voltage, since it is directly proportional to, it will be a straight line. The slope is nothing but the slope of the graph. So slope is nothing but K, because the slope is nothing but V by L, that is equal to K. So just to keep in mind here. So this is one of the expression in terms of the voltage. And another thing, you just see that The current delivered by the current delivered is delivered by the driver cell. That means current in the primary circuit is taken as to be I. Therefore, that current, as we discussed earlier, the current by the delivered by the cell is nothing but E net divided by R net. So here in the primary circuit only one cell is there of EMF ED, and the total resistance. This is the resistance R external, and the resistance offered by the total length of the potentiometer wire. Therefore, I can write that RAB. I can write that as to be RAB plus R external. Here we are assuming that the external resistance of this driver cell is negligible or 0. If you want to add this driver cell of internal resistance RD, then we can use that RD. If it is not there, then you can substitute that as to be as 0. So I is equal to E by R net. So by using this, V is equal to I into R, for the potentiometer wire, I into RAB. So here we can say that I is nothing but this value is there, and moreover you just see that K is equal to V by L. So if you want to write the expression for K, then we can write that K is equal to so the potential gradient throughout the length of the wire. So we can write that K is equal to VAB, VAB divided by LAB, the potential drop across this potentiometer wire. So that is equal to, this VAB is nothing but I into RAB divided by LAB by Ohm's law. So the voltage that can be written in terms of Ohm's law. Therefore, I can write that K is equal to RAB divided by LAB. This is nothing but a small r, resistance per unit length, into I value is there, that is E driver divided by RAB plus R external plus R internal of the driver cell. So this is the second formula for potential gradient. The another one is as we just now we said that V is equal to I into R, that is equal to I into rho L by A. That means where R means the resistance offered by the portion of the wire. Since as we stated here, for steady current means I will be constant. For the given wire of material, that rho will be constant resistivity, and for uniform wire A will be constant. Therefore, I can write that V is equal to I rho by A into L. So now this equation is compare with V is equal to KL. V is equal to KL. Then we can say that the another expression for K. So K is equal to in terms of I rho by area of cross section. So these are the three important relations for potential gradient, and this is the principle of the potential meter. What is the main purpose of potentiometer is to measure the potential difference. When compared to normal voltmeter, which one is used for generally for measuring the potential difference, here since this circuit is operating under the balancing condition where there is no current flow or current drawn from the secondary circuit, the cell connected in the secondary circuit, then we can get the accurate value when compared to the normal voltmeter. So that is the main purpose why potentiometer is more preferable than the ordinary voltmeter to measure the potential differences. So this is the explanation for the principle related to potentiometer. The another parameter what we are going to define in the potentiometer is called sensitivity. So what is sensitivity? The sensitivity means the ability to measure the smaller potential differences between the given 2 points. So therefore, S is generally inversely proportional to potential gradient. Since K is equal to V by L, there inversely proportional is nothing but proportional to L by V. So this is so from this we can say that S is proportional to L. So when the length of the potentiometer wire AB is increased, So that's why we are in general in lab we are using 10 meter as length of the potentiometer wire. So when length increases, the sensitivity of the potentiometer wire also can increase. Because of that you can measure even a smaller potential differences. Yes, that is the definition for the sensitivity of the given circuit. And another thing, there are some another important parameter or the things what we have to be mentioned here is, again you just consider this situation. Yes, I can draw that is another experimental circuit. Yes, say this is K1 and this is some variable resistance R external or rheostat, and this circuit is nothing but primary circuit or AB. This is the primary circuit. Now the secondary circuit is nothing but the cell of EMF E which is connected. This is some series resistance RS connected with the cell of EMF E, and there is a parallel or shunt resistance S connected parallel to this given cell. Say this is key K2 and then it is connected to G. So this is the experimental as a setup for the potentiometer. So as we said earlier, this will be E driver. Some important results we are going to give in this circuit. First one is, for the proper function of the circuit, that means in order to get the balancing length or balancing point, that means a zero deflection in the galvanometer. This is the very important condition. That means the driver cell EMF should be greater than the EMF of the cell used in the secondary circuit. Then only the circuit can used for the measurements. So this is the important condition. So driver cell EMF should be greater than E. And another thing is, they may ask in question, so what effect will there on the balancing length? Suppose this external resistance or there is a change in external resistances. Now you please see that when this R external increases, the balancing length also gets increased. Why this is means, when R external increases, the current through the primary circuit gets decreased. When current through the primary circuit decreases, the K value also decreases. Since K and L are inversely proportional, as K decreases means L should increases. So that's why here we are writing that R external increases means L will increase. In the case of what is the effect on this shunt resistance? Suppose the shunt resistance increases, or the parallel resistance connected with this as a cell, then the balancing length also gets increased. In this case, the terminal voltage of the cell will decreases. That terminal voltage should be same as to be voltage across these 2 points A and J. So where we know that V is equal to E minus IR. So in this case, as V decreases, we just see that for the given circuit K should be constant. Therefore, when the terminal voltage decreases, the corresponding the value of V will decrease. In order to maintain K has to be constant, L should be increased. Or we can simply say that where shunt resistance increases, the balancing length of the circuit gets increases. But what is the effect on this series resistance? When this is changed, L remains the same, L remains constant. So that means during at the balancing condition, the current passing through the resistor RS will be 0 because of the balancing condition. Then there is no current flow. So whatever the change has happened here, that will not affect the balancing length. So these are the important point what you have to be keep in mind. One is this point, E driver should be greater than EMF of the cell for the proper functioning. External resistance increases, balancing length will increase. Shunt resistance increases, balancing length will gets increases. When the resistance connected in series with the given cell change, there is no change in L value, balancing length value. So these are the important point we have to be keep in mind. Now next I am going to discuss the applications of potentiometer. applications of potentiometer what we are going to discuss. There are two circuits. One is based on experimental circuit, so better you can go with NCRT diagram. Yes, so these are the as a driver cell. Yes, say this is some K as a key K1. This is some variable resistance, say that is R external or RH, and this is the terminal A. You just redrawing the diagram in experimental as a point of view. This is terminal A, so this is like this, and this terminal is connected to a metallic strip here. You can see this apparatus in your lab. Therefore, yes, this is the another metallic strip. This length is 1 meter. This will be another 1 meter. Similarly, 10 segments will be there. Yes, like that it will go. So, yes, so in this manner it can be connected up to 10 segments. Okay, so yes, so this is the the given circuit. Now across this terminal A, the first application what we are going to discuss is comparison of EMF. So comparison of EMF of the cell. So comparison of the EMF of the cell. So for that reason I have to use two cells. So say this is a cell of EMF E1 and this is E2, plus minus will be there, which is connected to a special arrangement of the key. Say this is terminal 1, terminal 2, and this will be terminal 3, and it is connected to galvanometer, and then it is connected to jockey. Yes, now say this corresponding balancing length has to be L1 when 1 and 3 is connected. When 1 and 3 is connected, this cell of EMF E1 is connected in the circuit. Therefore we can get some balancing length. In that case I can write that E1 is proportional to L1. Now there is a contact between the terminals 2 and 3 at this time. So in this case the cell of EMF E2 is connected in the circuit. Therefore I can say that at the time the corresponding balancing length is stated as to be N2. Therefore we can say that is E2 is proportional to L2. So by dividing that 2 we can get that as the ratio E1 by E2, that is equal to L1 by L2. So this is the thing used for comparison of the EMF. Some cases in examination point of view, this L1 by L2, this is E1 by E2, that is equal to L1 by L2. This is the result. Some cases in questions they may use the series arrangement or parallel arrangements of the key. Batteries. There you can use the effective formula. That means E series equal to E1 plus E2, and if the polarities are reversed, you can inverse the sign. Yes, so that problem part that we will be discussed. The second application is to find the internal resistance. To find internal resistance. Okay, so this is the internal resistance of the given cell. For that, the arrangement of the circuit is very similar to this one with a slight modification. So this is K1, and this is some variable resistance or external, and this is connected to terminal A, and as we drawn earlier, so this is the segment A, and then it is connected to another segment, and then it is connected to another segment, so on. Like this you have to be, go with that, and this terminal is connected to here. So that is the general thing. Now please see that here, this is the given cell whose internal resistance we have to be find out, E, R, internal resistance of the cell. And there is a parallel resistance, shunt resistance. So this is some resistance R connected parallel with this as shown here. So therefore that will be connected with some key, say for example that is key K2. So this is key K2 is connected to a galvanometer. Yes, this is connected to a galvanometer. Yes. So when K2 is open, we can say that what is EMF, what is terminal voltage of the cell, that and all we discussed in the last lecture. So please kindly go and revise that if you have any doubt. Therefore, when K2 is open, then there is no current delivered by this through this external resistance. At the time what you are measuring is called EMF of the cell. Therefore, the corresponding balancing length is taken as to be L1. That is taken as to be L1. So you just see that this is corresponding balance length L1. Now when K2 is closed, so K2 is closed. When K2 is closed, what will happen? The current will be drawn from this cell. Therefore, at the time what you are measuring is, that is called terminal voltage. The corresponding balancing length is N2, or that points N2, and the balancing length is L2. Therefore, I can write that E by V, that is equal to L1 by L2. So this is the expression what we get. Then as we discussed earlier, the internal resistance formula, R is equal to small capital R, the resistance connected in parallel, E by V minus 1. So that is equal to, that E by V is found here has to be L1 by L2. Therefore, R into L1 by L2 minus 1. Since we said that during the discharging process, E is greater than V, therefore the corresponding value L1 should be greater than L2. So that is, since E is greater than V, therefore we can say that L1 is greater than L2. Then only the small r cannot be negative. So this is the another application of the potentiometer, which is used to find out the internal resistance of the given cells. I hope that you please note down this theory part, and in the next lectures we can discuss the additional topics which are related to MCQ point. For that, I am just directly going to give some formula. I am not going to discuss any derivation part for that. So since this is related to CBSE part, so I have discussed derivations. There are some other additional topics which is required for the JEE or NEET examination. For that, I can directly give the results. Then we will do the numericals or conceptual questions related to current electricity in the next video lectures. Thank you, students.